Okay, so let me take a look how we are doing. In the meantime, I wrote down these rules, which I think has been already covered with you before. So let me see. Or did you get it? Get something? Yes, that's exactly what. Most of you are still working on it, so that's. How did you do it? Yeah, that's the gradient. You can try the Hessian. Okay. So in the interest of time, I will show you how to do it by applying these rules. Yeah, the point is basically if you go this route, this route, and try to differentiate this directly per coordinate, it will, as some of you have found out, it will generate a lot of algebra, and this is a simple energy. This is a simple energy. When we become computing the Hessian of this, it will get more complicated, and the actual energy. This is the simplest physics-based model. We will be dealing with more complicated models, so that's why I think it's worth it to spend some time and understanding this multivariate calculus, because that organizes things a little bit better. So let me show you how. Can we do that? So here are these rules. I don't know if I need to go through that again. Probably not. I made some shortcuts. Yeah, one thing I would like to note is that the gradient is always evaluated at some point. Okay, like you could be writing the point there explicitly. I decided not to make the notation cumbersome. But always keep in mind that whatever differential operator you're evaluating, it's always at some given point, okay? In this case, we of course assume that the point is exactly our P and Q. So that's where we are differentiating, okay? Okay. So let's apply these rules. I guess let me make just one comment on these rules. The one thing I would like you to always check is that the dimensions agree, okay? So for example, here on the chain rule, so the gradient, aka Jacobian, whatever you want to call it, of H, whatever you want to call it, always it's going to be an M by K matrix, okay? The gradient of F will be an M by N matrix, evaluated where, by the way? At what point? Here it's slightly tricky, right? Like if I'm evaluating this at point X, then the G also will be evaluated at point X, but the gradient of F certainly cannot be evaluated at X because already the dimensions would not agree, because I need to evaluate this at Gx, right? It's sort of obvious, but that's the chain rule. And the dimensions of G would be N by K. So I see that everything is cool, because if I multiply M by N matrix by N by K matrix, I get M by K matrix. So that's what I have on the left. So that's good. So it matches, right? If it wouldn't, that would be a problem, because certainly that can't be true. It's sort of important here. So here is a scalar product of two functions. So f is a scalar function, multivariate scalar function, and G is a vector function. By the way, by default, I always assume that these are column vectors. Okay, so like this M is to be interpreted as M by 1. So a column vector like this, okay, of M entries. And the gradient, I always assume that's a row vector. Unless it's a multivariate one, is Jacobian, but then the row vectors are the gradients of the individual components of the function, okay? So here, let's make the type check here. So the gradient of H must be an M by N matrix. So f is just the function itself. So what is the f? What is the dimensions of f? That's just a scalar, right? So that's just 1 by 1, okay? The gradient of g, that's m by n. So this is a scalar times matrix. Okay, that's where you are starting to see the difference between the regular one-dimensional single variate calculus and this multivariate calculus. G. So what is g? G is an m by 1 vector, right? And the gradient of f is a 1 by n vector. Okay, everybody knows how this product is called. The outer product. It's like the bigger brother of the inner product. So it's just a regular matrix product, right? Which produces m by n matrix. Here I have m by n matrix. If I sum them, I get m by n matrix back. So everything is cool, right? If somebody was trying to tell you that no, this rule should be just like the single variate calculus rule, like this, then you can immediately prove them wrong, right? Because this would be 1 by n. This would be m by 1. There is no way I can multiply this, so nothing like this could possibly work. That's why I'm always taking care that the dimensions agree. If they don't agree, nothing can be right. Oh, let's do it here too, as we already got a kick of it. So this is m by n. G transpose is what? So this is G transpose will be 1 by m. The gradient of f is an m by n matrix. F transpose, what is fm? So that would be 1 by m. And the gradient of g is m by n. So here I somehow don't have it right because the h was supposed to be 1 by n and not m by n. Okay? So this is for the dot product. Then I believe covered these rules. Okay? So everybody cool with that? So let me show you how to apply these rules to compute the Hooke's law, the potential due to Hooke's law. So let me remind you what that was. So that was P minus Q minus L0 squared. Okay? And let me take baby steps in case this is the first time you are seeing this. Actually, let me see. Did somebody teach you this before in your calculus class? So you did, but you had a training in Russia. Anyone else? Yeah, my calculus also was not like, I mean, we did not have these multivariate calculus rules. So I guess you want to go to Russia for your math training. But it's not so bad. You can learn it fairly easily. So let me take baby steps. Okay. So first, let's just compute the gradient with respect to p. Okay. So that means we will assume that the q is fixed. Okay. And the one with respect to q will be similar. We'll do that in a second. So this will be a 1 by 3 vector. Okay. So let's first take a look. What is the structure of this thing? If you think about it for a second, we can write this as a composition of two functions. I'm really taking baby steps here, okay? So function 1, and I assume q is fixed, okay? Now, I assume q is constant, and I'm differentiating just with respect to p, all right? So the f1 function would be compute the squared norm of p minus q. In other words, that's p minus q transpose times p minus q, all right? That's function number 1. And function number 2 would be just, I guess we can still, let's do it really carefully this time. So this function has this signature, maps a 3-dimensional vector to R. And the function f2 is just a scalar function, and it does this. Square root of x minus L0 squared. So f2 is a function, just a scalar function. Nothing could be simpler than that, okay? And then my potential, which I'm trying to differentiate now, is just a composition of these two functions. Everybody agrees? Because if I take this and I plug it in here, I get exactly my expression, right? That's, by the way, how, well, okay, maybe I'm getting ahead of myself, but if you ever get to work with some automatic differentiation software or even symbolic differentiation thing, this is how it essentially works. It breaks it down into like the graph, the structure of the expression, and then it just applies the individual calculus rules and chain rules to put it together. So we will do that on this example. So basically it's a composition of two relatively simple functions. To differentiate f2, that should be an easy matter for everyone. Okay, so let me do that real quick. So if I differentiate this, I will get, what will I get? So I'll get square root of x minus L0, and I can put the 1/2 back because here I will have 1 over square root of x0, which is 1/2 of 1 minus L0 divided by square root of x. I assume that everybody knows single variable differentiation. That's for granted. Let me also prepare the gradient of f1. Okay. Here it's sort of silly, but here we can already apply the dot product rule. This one. It's sort of silly because you could also it's such a simple multivariate function that you could also see it directly. But as an exercise, we can just apply this rule. And what we will, so this is the dot product of two functions, p minus q, right? So this one, they are both the same, so it doesn't make a difference if it's f or g. So in both cases, it will be p minus q transpose times the gradient of p minus q. And the second thing will be exactly the same. So p minus q transpose again, gradient p minus q. Okay? What is this? Gradient of p with respect to p. That's an identity matrix, specifically 3 by 3 identity matrix. And if I multiply the vector with it, it doesn't really do anything. So that just goes away, and the result is 2p minus q transpose. Okay. And using this, let's see if I can still squeeze it in there. I can compute the final gradient, at least with respect to p. So here I just apply the chain rule. Okay. And the chain rule says that I first have to differentiate f2 at the point f1 pq, and then differentiate whatever was inside. So then I do the gradient of f1. Okay. And if I plug in the expressions I've already prepared here, then I plug in the formula for the derivative of f1. So this will be 1/2 of 1 minus L0, and square root of x, in this case x is the f1 of pq, f1 is the squared norm, so this will be norm p minus q. Okay. And the gradient of f1 with respect to p, that's what I computed just here. So this is exactly 2 times p minus q transposed. So if you let me call this L, the norm of p minus q, so I can simplify it and write 1 minus L0 divided by L times p minus q transpose. Whether transpose doesn't really mean anything, that's just because we said that the gradients will be row vectors by convention. And that's it. That's at least the gradient with respect to p. Okay, so if you compare it to the route when we were differentiating this expression directly, here I was doing it like really slowly, but you can do it. You don't have to be writing all these things I was writing here, and you can directly arrive to this expression just like that. After you get some practice with this stuff, of course. Oh, this, of course, let me just point out, this, of course, is a scalar, right? 1 by 1, L0 and L, they are both a scalar. And you can, maybe I should first do what is the gradient of E with respect to Q? So let me just do this quicker. It's gonna be almost the same thing. The only difference will be when I will be differentiating this with respect to Q, I will be taking the gradient of this expression with respect to Q. So in this case, it will be the minus identity, okay, because I have minus Q here. So what I will get this minus. So what I will get at the end of the day would be the gradient with respect to Q will be exactly minus this thing. So it will be, if you want me to write it, Q minus P transpose, but that's exactly the same as minus the gradient with respect to P. And that's exactly what we expected, right, from the physics interpretation, because if one force points like this, the other one has to be exactly opposite. But here we don't have to rely on any intuition or anything. You really just get it from differentiation. You can really write down the hard math. It's no like opinion or anything like that. Okay, if I wanted the gradient of E, then I would just put both of them together, and I would get the 1/6 vector. That's just a technical matter. Okay. Well, I guess the other thing you can realize here, that the directions of the forces also make sense, right? Because if L is greater than L0, what does that mean? That means that 1 minus L0 divided by L will be what? Will be less than 0, right? Will be negative. So that's the, oh wait, sorry. I did that wrong. L is greater than L0. This means that this will be greater than 0. Make sure I'm doing it right. So that means that L0 divided by L is less than 1. So that means this will be greater than 0. That's right. And that's the case of stretching of the spring. Okay, that's the case when I stretch the spring, and that's when the forces point this way, because this coefficient here, that's this thing here, that's positive. So this is my P, this is my Q. Then the negative grade, the force is the negative gradient, right? You must not forget this. The gradient points in the direction of steepest ascent of the energy, but force points in the direction of steepest descent. So we need to put the minus there. That's how it works. The force is the minus gradient, just like you would expect. Now, if I have compression, so if my current length is smaller than my rest length, then this expression, that's the coefficient here, that becomes less than 0. And that means it's pointing the other direction, right? That's this case. If I compress the spring, then the forces are pointing away. It always wants to go back to the rest pose. So indeed, this expression does what we would expect from forces to do. So the differentiation indeed works. Everybody cool with that? Any questions here? Okay, so let's do the Hessian now. So why do we care about the Hessian? We will care about the Hessian a lot when we will talk about implicit time integration. Okay. So we'll talk about that later. You will soon find out that explicit time integration doesn't work so well, and we will need to move to implicit time integration, which needs one order of derivatives more. That means going to the Hessian. Intuitively, what does it mean to go to the Hessian? It means to find a linear approximation of the gradient. So now we found the gradient at P and Q. Okay. And what if I told you, well, actually, I would need to know the gradient at P plus delta P and Q plus delta Q, where delta P and delta Q are some small perturbations away from that, yes?
I'm sorry, could we go back to the previous one?
Sure.
I wanted to understand from this picture what it means.
This one?
Yes. Just in general about why do you need to start from the energy? I mean, if you're simulating, say, for example, a spring, do you really start from the energy, or do you start from the force itself?
That's a good question. You could certainly start from the force. If somebody gives you the formula for the force, you certainly can start from the force, yes. But in many cases, the energy is the easier thing to come up with, and then the force you can just get by differentiation of it. It's actually a good question in general, because you can either, we will get to that later, but you can either be looking, so when we will be actually simulating something, we will be either solving systems of nonlinear actuations involving forces, or we will be solving optimization problems involving energies. These two views are equivalent. You can think about it one way or the other. I slightly prefer the energy one because it has certain advantages which we will learn later as we talk more about integration methods. You're absolutely right. If somebody tells you that the formula for, that's a very good question. If somebody tells you the formula for the force of the spring, then you can just be using that, right? I mean, if somebody tells you also the Hessian, then you can be using that too, but you might be wondering if that's really correct. So that's why one might not know this, so you can verify it, right?
I'm thinking from the point of view of an artist, if they had a system inside, say, some animation package, and then you give them a fluid, I don't think they intuitively think of it in terms of, let me apply an energy of 500 kilojoules on it, and what happens to the system. I kind of wonder they would think, let me apply a force in this direction, and let's see what happens to it.
Right, yeah. I mean, sure. In that case, in the system, all these things are already built in, right? But what we are learning here is how you can actually build such a system or modify it in a non-trivial way, right? You can always like approach the system like a black box, not knowing what is happening inside, and just like poke it and see what happens, right? But usually it's good to understand what exactly is going on inside and what are the units of the things that are happening inside. If you want to couple it with some like real world material, with some measurements like material scientist or somebody did, then you want to feed it in the right units and so on. So yeah, from purely artistic point of view, you don't really need this if you want to just like play with some existing simulator. But this goes deeper than that. This tells you how to actually build a simulator in the first place. Yeah, and big part of building it is to be able to differentiate your expressions, so you can then code them. Yeah, if you I won't really be talking about like these artistic perspectives on things. This will be really more about the technical things and the math stuff. So I hope you won't be disappointed. There will certainly be some amount of creativity involved, but more in the sense how you apply these technical concepts to create something interesting. And it's not like you always need some sort of creativity on top of the math. But this is certainly not like an art class or anything like that. So. Okay, so any other questions? So the Hessian will be useful to us if we want to at least approximate the gradient at a point p plus delta p and q plus delta q. Then we can do it using the Hessian like this. So we already computed the gradient at p and q. Okay, we know this is our 1/6 vector. And now if I just perturb it just a little bit, the delta p and delta q is small, then I can just write a vector out of them. It will be 1/6 vector. And I multiply it by the Hessian. Okay, that's a 6x6 matrix. Everything is cool. And this way I get a fairly good approximation of what the gradient at a small neighborhood of my point P and Q is. So that's exactly what will be used in implicit time integration. So this is just to give you a motivation why the Hessian is important. Or you can just trust me that you will need it. Okay, so how do we compute it for the spring? Maybe let me get a new paper. So the Hessian basically just means differentiating the gradient again. Okay. So this is really an exercise in multivariate differentiation. So if I just bring up the gradient again and I transpose it to bring it back to column vector, because our rules are assuming a column vector. So the formula we ended up with looked like this. So since I transpose it, this will be a column vector. Okay. So the gradient, and let's do it with respect to P. We can then discuss the remaining ones. So that's a mapping from R3 to R3. Here I made this a column vector, so 3 by 1 if you would like, just to be consistent with my notation. So that's what we have just computed, okay? And what I want to compute now is to differentiate this again. So compute the gradient of the gradient, okay? That's exactly at least the first block of the Hessian, the PP block, okay? So I guess I should explain that the Hessian is a 6 by 6 matrix which has 4 blocks: the PP block, PQ block. This is gonna be also PQ because from calculus we know that the Hessian is always symmetric matrix, so these two guys must always be the same, and a QQ block, okay? So let's first compute the PP one, and the remaining ones we will see soon, they will be similar. Focused enough? Okay. Right. Lighting was a little bit better. So what I'm doing here, I'm taking computing a gradient or Jacobian of a multivariate function, right? It's a function from R3 to R3. So indeed, what I will get here is going to be a 3 by 3 matrix. Okay, so now we go like one level higher. We go to matrices. You can go even higher, and we will actually need to some point later, but that goes to tensor. So I will save that for later because I don't want to scare you prematurely. Just kidding. It's not so scary. Okay, so how do we do this? It's the same story as before. We just apply the multivariate calculus rules. So again, we assume that the Q is constant here, and we are differentiating this expression just with respect to P. Okay. And we see that we have, let's again just break it down into some simpler terms. So this is a product of two terms, right? The P minus Q, that's as simple as it gets. And then we have something a little bit more funny going on here. So let me again simplify it using a scalar function. So I will again do baby steps, okay? But once you get a practice of this, you don't have to be like introducing these intermediate functions and stuff. So this will be a function that will essentially do this first part of the expression, the first term. So this will be a scalar function. It just computes 1 minus L0 divided by square root of x, where x is the parameter of the function. And then if you still remember the f1 function of p, because I assume that q is already constant. So the function f1, what was f1? F1 was the square norm of p minus q, right? That's what we computed before. So I'll just put it here. Or that's what we used before, so I can just reuse it. And the gradient of this was 2p minus q transposed, okay? So let's differentiate it f3. That should be a simple matter, I hope. You know what, let's first rewrite it a little bit. So f3 is 1 minus L0 x to minus 1/2, so the derivative will be 1/2 L0 1 over square root of x cubed. Does everybody agree with my calculus? It has been a while since I had calculus, but I think this is still correct. Okay, so now let's do this. So let's compute the gradient with respect to P of the gradient of E transpose. So that's this expression, okay? So it's a scalar times vector. So we will use the product rule, the first product rule here. I'm gonna do this. This is how I do this. I'm doing it really slowly so that you can, for pedagogical purposes. Okay, so oh, I guess you know what, even better would be to first write this using my F3 and F1. So this would be the F3 from F1 of P times P minus Q. Okay. So if I feed this into this function, I get exactly the first term times the second term. Okay, it really just isolated to apply it by the book. And then we're going to apply this product rule. So the product rule I first copy the F3 and F1 out of P. There's just P because I assume that Q is constant, so it's not a variable anymore. And then I need to take the gradient of G. So that's the gradient with respect to P of P minus Q, right? Because the G, this G here is this term here, okay? Now the second thing is that I take this term, P minus Q, and now I need to take the gradient of F, okay? So to get the gradient of F, I have to apply the chain rule. So it will be F3 out of F1 P, that's the first part of the chain rule, and the gradient of F1 with respect to, I don't really write this. It is at the point P, but I'm omitting that because we know that. Okay, so that's it, and now I need to just plug back in everything. So if you, again, let me use the shortcut that L is P minus Q. So the F3, what is this? So F3 was here. I don't need this anymore. So F3 of Fp is 1 minus L0 divided by the norm of P minus Q, but that's L. Okay, so this is this part. Are you with me? And the gradient of P minus Q, that's what we had before. What was that? The gradient of P minus Q? Identity, yeah. So I'll put there I3 to remind us that this is a 3 by 3 identity, okay? So what about this guy here? So that's P minus Q. I will just copy that. And here we have the derivative of F3, so that's what I prepared here. Evaluated at F1P. So the F1P is the P minus Q squared. So the square goes away, and I will have there the norm of P minus Q cubed, which, if I'm not mistaken, is L cubed. Okay, so I will get there 1/2 L0 1 over L cubed. Is that correct? I think so. And so that was this piece. And the last piece is the gradient of F1 with respect to P. That's what I have prepared here. So that's 2P minus Q transposed. Okay. So conveniently we see that these halves they cancel out. So that's nice. And if I make it a little bit neater, I will see that I'll just copy this term for now. And what I will find here is this is L0 divided by L cubed, P minus Q transposed. Okay. First thing I should do is to make sure that my types are correct. Okay, so this is a scalar. This is a 3 by 3 identity, so scalar by matrix. That's cool. This is another scalar. P minus Q, this is a 3 by 1 column vector, and P minus Q is 1 by 3 column vector. Okay, so this is a funny type of outer product, but it's a 3 by 3 matrix, so everything is correct, at least from the type perspective. Because I expected to get a 3 by 3 matrix, and I got a 3 by 3 matrix back. It's not such a terrible 3 by 3 matrix, right? Actually, sort of interesting 3 by 3 matrix if you think about it, right? It's a linear combination of an identity and an outer product matrix. Maybe if you are staring at it for a while, then maybe you could see some geometric meaning at it, and then help us improve our paper with Tintin and mass spring systems, because that's closely related to this baby here. That's the solution, at least the first part of the solution. But it turns out that the remaining ones are actually quite simple. So if I did the same derivation if I differentiate the spring force with respect to Q, it turns out, so this would be, we can denote this as PQ Hessian of E. It turns out this is nothing but the minus of the one we have just computed. So it's exactly the same thing except for opposite sign. Yeah, I don't think I have the time to go through it again. If you want to, if you want to do that for homework, you can go through. You can do it by yourselves, and see that you arrive to the same expression with an extra minus over there. And for the last one, we know that these two are the same because the Hessian is always symmetric, no matter what. It's always symmetric. That's directly from the properties of partial derivatives. Partial with respect to x with respect to y is the same as partial with respect to y and with respect to x. That's a calculus thing. And this is exactly the same as this. So actually the block form of the Hessian, if this is like my block B, the block form is super simple because it's just B, and B, okay? So basically the same block repeated 4 times, and the off-diagonal ones are multiplied by -1. So that's the Hessian of a single spring. That's basically the end of the story, as long as the derivatives are concerned. For us in the physics-based simulation, is actually the beginning of the story, because what we do now is we take these derivatives and we then plug them into a simulator, and that allows us to do time integration, which is something which we will talk about later. Not that much later. Okay, one thing I would like you to always keep in mind is that you should always be checking for mistakes. How do I know I did not make a mistake? Did I make a mistake?
No, just a question. I couldn't understand how L0 by L cubed was going to a dimensionality of 1 times 3.
Oh, sorry. Yeah, sorry. That was supposed to be 1 by 1. I'm sorry. Otherwise, it wouldn't work, right? This is supposed to be scalar by matrix. Yeah, good. Yeah, I made a mistake. See, my point was it was mistake on purpose, because my point was you should always check for mistakes, right? It's easy to get this wrong if you're doing it by hand. There's some software that can do this for you, but I don't know if there is any software. There is like the Maple and Mathematica, maybe even MATLAB has some. Huh?
Wolfram Alpha, maybe.
That's Mathematica, no? Or
Yeah.
Right.
Yeah, Mathematica is the
Right.
software.
I was never able to find if they actually support this multivariate differentiation. They can certainly do like the regular type of differentiation. They have no problem like churning expressions like this. And some people actually do it, like some researchers in physics do it exactly this way. They just like spit out a piece of expressions, feed it into Mathematica or Maple or anything, and just hit differentiate, right? And that's just turning the crank. And what it spits out is a mess, typically, right? For some more complicated expressions. Because the derivatives, they typically grow in complexity, right? The software sometimes can apply some symbolic substitutions to like simplify expressions like x divided by x equals 0 and so on, right? But usually it's a big mess, and you basically don't see what happened there. Because there can be like several pages worth of expressions. It's sure you can implement them, right? but if first of all, it can be missing some opportunities for cancellation, and second, you don't really see what the expressions actually are. If you write it down like this, you can you can see and you can reason about the geometry of what's happening. And also, I think you should be checking for potential errors no matter what. Oh, see, I'm sorry, I'm trying to cover two things at the same time because I'm trying to rush by the end of the class. I'm not sure if any of these packages actually supports multivariate differentiation. If any of these packages could give you a neat result like this. More likely, what they can do is give you a mess of formulas, which will be absolutely correct derivatives. But the notation is a disaster because you lose the structure, you lose the matrix vector structure, and instead you just have to go to individual indices. So there will be very long expressions. You can try it if you want. I don't know if you know any symbolic differentiation package that actually supports a multivariate differentiation, matrix vector calculus. When I looked for it, I couldn't find anything that would actually do it. There's another possibility which is called automatic differentiation, which is sort of cool. I didn't play with it much, so I don't have much experience. I know some people use it with great success. Automatic differentiation is different from symbolic differentiation. It's basically like a programming language abuse, if you will, typically using some templates in C++ or something. And you give it a function with some special types with some templated types. And the differentiation happens for you at compile time. For a code of a function is for you transformed for a code that computes the derivative of the function. It's pretty cool. I don't know how well it works, and I'm always a little bit worried that it'll also miss some opportunities for cancellations. Like if you get some x divided by x, if that's not canceled away, then good luck evaluating close to 0, right? So what I recommend, what I do have experience with is this, basically do it by hand. And once you get some experience with this, it's relatively easy. But then what you need to do is to check that you actually did it right? So how do you check? Well, fortunately, that's quite simple. Essentially, this approach is called like finite difference check. So if I have a function which is Rn to Rm, let me just finish it real quick. And I pick some random unit direction vector. Then I know that for x plus epsilon d, where epsilon is some small scalar, yeah, even for a big one, this would actually be still correct, but it's mostly useful for the small one. So from Taylor expansion, or that's essentially what the gradient is. That's the whole point of a gradient. It's basically a good approximation of the function close to the point where I evaluated the gradient. Okay, and good, I can actually put an upper bound on it. Good up to epsilon squared. Okay, so that means if you, okay, I guess I'm rushing it, but hopefully it will make sense. If not right now, then at least when you are coding it up. This should be something that's O of epsilon squared, which basically means that should be bounded by some constant c times epsilon squared. Okay. So what you are gonna do is to test it, to test your code after you have implemented some function, for example, the Hooke's law, and you implemented the derivatives of it. Then you can use this expression to actually test it. Basically, what this means is you are testing, you are trying to perturb, you compute the gradient at some x, you perturb a little bit, and you see if your gradient is a good approximation of the function after the perturbation. Okay? Because that's really the intuition behind the gradient. It's a local linearization of a function, right? Like Tintin was showing, if this is my x, locally, at least at some small neighborhood, the values of the function, the actual values of the function should not be far away, right, from the linear approximation. And not far away, that's quadratically not far away by this epsilon squared. So what you're going to do is you're going to try some epsilon. You pick a random d. You're going to try some epsilons like 0.1, 0.01, 0.001, and so on. And what you should see after you evaluate this expression, this should be going down quadratically, right? With some constant which you don't know, but if you plot it, I hope I'm doing this right, if I plot minus logarithm epsilon and minus logarithm, if I call this t epsilon, let's call this t epsilon, so you should see something like a parabola, right? Because it should go, the accuracy should be improving quadratically. It'd be cool if actually somebody wanted to try this for a spring and tell me, if it worked out. It should in theory. So the main point is, I mean, you can also test it with different, you can just try a finite difference just with a single epsilon. Like if you're in doubles, then I think like 10 to minus 8 or 6 is a reasonably good epsilon. You don't want to go too small because then you'll be running into rounding errors, into numerical precision issues, and you don't want to go too big, so you are really in a small neighborhood. So that's why I suggest to like try multiple epsilons and see if it's really improving roughly quadratically your accuracy. If that's the case, you probably got it right. If this is really far off, like by a landslide, you probably made a mistake somewhere. Okay. So I think this is a good point to quit, unless you have some questions. Okay, so we will meet again on Wednesday. All right. Thank you.